Good day, everyone, professor and classmate. Today I am excited to present our final project for deep learning theory and practice. The title of the presentation is Transfer Learning on a Data Efficient Image Classification Benchmark. My name is Wang Kaiwen, and I'm from Department of Computer Science and Information Engineering at National Jinan University. Uh, in this one, project background and core pain points. Let's start with the background and the core problem we are trying to solve. As we know, deep learning models are notoriously data hungry, typically requiring thousands or millions of labeled images to perform well. However, when we look at specialized fields like medical imaging, obtaining high quality labeled data is exceptionally difficult, time consuming, and expensive. And for this dataset and 7 major categories. Moving on to our dataset, the ISIC dataset focus on skin lesions classification, which holds massive clinical value because it covers both skin cancers and beneath lesions. The dataset is divided into 7 major categories. The first one is MEL, NV, BCC, AKIEC, BKL, DF, and the last one is VASC. To simulate a data efficient environment, we strictly limit our data splitting strategy. We use Python to randomly shuffle and build an evenly distributed subset, just 350 training images and 210 validation image. That means we have exactly 50 training image and 30 validation image per class. Small dataset splitting strategy. Now let's talk about the models we test. Our baseline is ResNet 50, a 50-layer deep residual network. Its key strength lies in its residual skip connections, which allow gradients to flow directly backward. And for comparison, we choose GoogleNet. Unlike ResNet, GoogleNet relies on a 22-layer inception architecture. Instead of just going deeper, it uses multi-scale parallel convolutions, carrying a parameter count that is only about one-third of ResNet 50. When dealing with only 50 images per class, overfitting is an immediate threat. To defend against this, we embed a robust image augmentation strategy directly into our MATLAB training pipeline. We applied random horizontal flips to simulate mirror symmetry in the lesions. We also utilized random translation augmentation and to randomly shift the lesion positions. Let's look at the actual outcomes. Using identical hyperparameters, a learning rate of 5 times 10, ResNet achieved a validation accuracy of 62.86%. Meanwhile, GoogleNet fell behind at 57.62%. For context, the original paper baseline for fully tuned ResNet 50 under this setup hits a balanced accuracy of 66.19%. Our key findings showed that while GoogleNet is lighter, ResNet 50 residual connections stabilized faster and handled spatial features better in an extreme small data environment. Now, to conclude, this project provided us with 3 invaluable takeaways. First, we mastered the end-to-end MATLAB transfer learning workflow, successfully modifying final classification layers to repurpose massive pre-trained network for niche tasks. And second, we witnessed the monumental impact of data augmentation. And finally, we validated the practical philosophy of TUNIT. Real-world AI excellence isn't about blindly throwing more parameters or complex architectures at a problem. It's about careful hyperparameter tuning and data engineering. Thank you for your time, Professor. I welcome any questions you may have.